I need a heatsink or not? So in a previous video I mentioned that there were three aspects that should be considered with respect to whether you choose or choose not to use a heatsink relative to thermal performance. So these three are in no specific order of importance, and they are a degradation of output, in other words less light or less photons. Secondly, a chromatic shift or change in colour. And thirdly, the performance of the lead in terms of efficacy. This is the efficiency of the lead. Most folks will read that as lumens per watt, but for grow folk it should be considered in terms of micromoles per joule. So what I've got is three slides that are pretty useful in demonstrating those particular issues. What I should say is that these slides are lead tests based in real time, so the information is based on taking a single lead, driving it, and then generating some key metric data about thermal performance. So let's consider first what occurs in real time, and later can talk about lifetime data and what happens over time, which I'm sure is more important to you as a builder rather than the sort of immediate impact of when you first turn your grow light on. So on the first slide, what I'm going to show you relates to the degradation of output, the reduction of light. The chart is a two-axis chart. X-axis is wavelength, and on the y-axis is spectral power over wavelength. This is the surface illuminance over colour. And as you can see, this lead is peaking roughly around 450 nanometers, so it's a royal blue LED. And what are we looking at? So the lead peak output is at 15 degrees C, so that's its best performance, which is a somewhat unrealistic temperature to try to maintain. Unless your heatsink is an icy pole. As the lead starts to build temperature and the graph goes to a maximum of 75 degrees, you can see that the surface illuminance or milliwatts per nanometer starts to degrade as a consequence of temperature. So to restate, this is real-time data and is not an extended life. So the takeaway from this is that the lead output is reducing as a consequence of heat. Next point, color shift. So on this chart we have a graph, we have a two-axis chart again. X-axis we have temperature in Celsius. I'm afraid most of this information is in Celsius, so apologies to those that live in the world of Fahrenheit. And the y-axis is wavelength, in other words colour. And again, this is based on the same 450 nanometer royal blue LED. I think at this point I need to highlight that the next two graphs have tables that clarify the data points and need some explanation. So this study is using pulse, or PWM, or pulse width modulation, to power the LED. So T-pulse is the time of the pulse, and that's shown as various data points of time in microseconds. I'm only focusing on the most revealing data point, the purple line of 20 microseconds. While the use of variable pulse widths is a whole area of study and beyond this video's scope, it's worth noting that notionally there is an idea that wider pulse widths at higher drive can get you more light at less heat within the constraints of not producing some fairly annoying flicker. Although do plants actually really care about flicker? Could we light plants with 1 second bursts of light with no impact on plant morphology or outcomes? The chart on colour shift, what we can see here is that around 15 degrees C or Celsius, the chip is producing light that's just under 448 nanometers. But then as the temperature starts to increase and we get to 75 C, which is a pretty decent jump, the chip is actually approaching 450 nanometers. So when it's running cool, it's about 2 nanometers off its spectral peak of 450 nanometers. So here we have a lead running in real time that has experienced a shift in color due to temperature variations. So now if we move on to point 3 and talk about lead efficacy of the last graph, it's from the same study, where we show on the x-axis the temperature in Celsius, and on the y-axis lead efficiency in percentage terms. And we can see at low temperatures, typically less than 20 degrees, we can see that the lead is approximately 28 to 29% efficient. That's lead efficiency. As the chip increases in temperature at the junction, that efficacy starts to fall away. And if we kind of follow the bouncing ball, we can see that around 75 degrees, the chip has lost approximately 2.5 to 3% of its efficiency. Let's return to the original question. Is a heatsink important with respect to the performance of your lead strip grow? The previous few slides definitely point to some issues with heat during operation. However, its performance over time, which ultimately will impact yields in terms of quality and quantity of biomass or whatever material growing, is more interesting. It's what occurs over the longer period of time that we probably need to spend a little time focusing on. Let's consider that in terms of longer term performance data. So prior to considering long-term and life summary data on LEDs, there is an important note that we should make. So the data that we've demonstrated to this point was real-time data, and the data was based on an EZ900 Cree blue 450 nanometer chip, and the temperatures were really based around the junction temperatures. When we look at the lead strips that we and other people supply that are nominally white, these are chips that have had phosphor applied to the underlying blue chips. And the important thing to note here is that the phosphor can in fact be 20, 30 degrees Celsius higher than the junction temperature of the chip itself. It's an important thing to note with respect to possible implications to phosphor degradation and how that impacts our 3 points, and what impact or effect a heatsink will have on that performance.